Okay, then welcome everyone to the last part of the symposium. Then now we have Valeria Rios, and she will talk about the independent orbital 3D.
Okay, thank you. So I'm going to talk about the independent orbital-free DFT for nanoparticles. So in constant DFT, the system of reference is a system of non-interacting fermions that experience an effective potential and have the same electron density as the real system. For orbital-free DFT, the system of reference is a system of non-interacting bosons that experience an effective potential called the bosonic potential and have the same electron density as the real system and the constant system. Now, in orbital-free DFT, we exploit the same functional for the total energy as in constant DFT, contains the Hartree energy, the non-interacting kinetic energy, exchange correlation, and electron-nuclear interaction. In constant DFT, the non-interacting kinetic energy is expressed in terms of the constant orbitals, while in orbital-free DFT is a functional that depends explicitly on the electron density. So under certain approximations, this method scales linearly with the system size. Now, by doing variation and minimization of this functional subject to the constraint of n representability, we get the ground state density of our system. This variation and minimization allows to write eigenvalue problems for both systems, the fermion constant system, which is the system of reference for the constant DFT, and the boson constant system, which is a system of reference for orbital-free DFT. Now, in the fermion constant system, we have a Hamiltonian that contains the kinetic energy operator and the effective potential Vs. This Hamiltonian allows to have multiple solutions, meaning multiple wave functions. A similar scenario we can observe for the boson constant Hamiltonian where we add the Pauli potential, and this Hamiltonian allows to have multiple solutions as well. So now that we know that both Hamiltonians admits multiple solutions, we want to study the common LUMO for both systems. Now, in the real system, the fundamental gap is given by the difference of the ionization potential minus the electron affinity. In constant DFT, if we remove a partial electron, this will come from the HOMO, the highest occupied molecular orbital. And if we add a partial electron to the system, this partial electron will sit in the LUMO. If we take the energy difference of the HOMO and LUMO, this is not going to be equal as the fundamental gap of the real system. In that case, the exchange correlation potential needs to have an derivative discontinuity. Now, in the boson constant system, the scenario is different. If we remove an electron, this electron will come again from the HOMO, but if we add a partial electron, this electron will sit in the HOMO again. This is because the boson constant system, the ground state of the boson constant system does not obey a Pauli principle, so it can be n times occupied. Now, if we want to recover the gap for the fermion constant system, the Pauli potential must have a derivative discontinuity. On top of that, if we want to recover the fundamental gap of the real system, then we add the derivative discontinuity of the exchange correlation potential. So this is an indicative that the fermion constant system and the boson constant system both have orbitals. So now we can explore other theories in the time regime, such as TDDFT. So we know in TDDFT we have the time-dependent constant equation where Vs depends on time, as well as the constant wave function. The effective potential contains the Hartree exchange correlation depending on time and the externally applied potential. The exchange correlation potential that depends on time ensures that the dynamics of the constant system is the same as the dynamics of the real system. We can approximate this potential using the adiabatic approximation, in which we take the ground state exchange correlation potential, and we evaluated in a density at a density at a certain time. Now, there is an analog set of equations for the boson-constant system where the effective potential VB depends also in time, the wave function depends on time, and we add the constant potential plus the Pauli potential. Now, this Pauli potential ensures that the dynamics of the orbital-free system is the same as the dynamics of the constant system. We can also do an adiabatic approximation of this Pauli potential, taking again the ground state potential and evaluated at density at time t. Now, in practice, solving the time-dependent constant equations is not fully necessary if we want to study the excitation spectrum of a system. For that, we can use the linear response theory. So in linear response theory, we know that if we perturb a system at some point in space and time, we can observe the response of the system at another point at a later time. So in that case, mathematically, we are observing the response of the electron density that couples linearly with the weak perturbation V1. Now, the response of the electron density in the real system must be the same as the response of the electron density in the constant system and in the orbital-free system. Now we know that the response functions for the three systems is different. In that case, we use a different perturbing potential. For the constant DFT, the constant system, we have BS1. For the orbital-free system, we have BB1. Now, equating these equations, we are able to write the Dyson equations that relates the response of the real system with the response of the constant system. And we add a correction to the constant response system to get the excitations of the real system. So we add the Hartree Pauli and the exchange correlation, the Hartree kernel and the exchange correlation kernel, where this is the functional derivative of the exchange correlation potential. Now, if we want to recover the excitations of the constant system from the boson constant system, then we need to add as well a correction given by the Pauli kernel, which is the functional derivative of the Pauli potential. Okay, these equations can be cast in a matrix form called the Cassidy equation, where we have the response of the electron density given by the multiplication of occupied and unoccupied orbitals, and the eigenvectors of the anti-Hermitian Cassidy matrix. So these are the matrix blocks A and B. This gives us the excitations. A gives us the excitations of the non-interactive system plus a correction for the interacting system. This is the coupling matrix. Then we have the B block matrix that describes the excitations in the system. There is another form to recast, to reformulate the Cassidy equation by setting the wave functions to be real, the exchange correlation kernel and the Pauli kernel to be frequency independent. So in that case, we have A and B becoming real, and we can reformulate this Cassidy equation in this way, which is gonna be helpful for our previous next discussion. So these are the frequencies of the real system. This is the coupling matrix, and these are the frequencies of the non-interactive system. So now, let's study what type of excitations we observe for each system. So I'm gonna recall to this equation during my discussion. In this cartoon, I'm showing this side, I'm showing the ground state of three systems. For the real system, we can observe any kind of excitations. For the Fermi constant system, the determinant can give us only single excitations. In the boson constant system, because the ground state is unoccupied, any perturbation will affect all the electrons or the collective excitations, which resemble into plasmonic excitations. Now, here I mentioned that the coupling matrix is given by the double integral of multiplication of occupied and unoccupied orbitals and this kernel. This kernel can be dependent on which system you want to link the Hartree exchange correlation, Pauli or Pauli-Hartree exchange correlation. We can define the Pauli kernel as the addition of the adiabatic plus the non-adiabatic, which is frequency dependent. Okay, that in case if we want to recover these excitations of the fermion constant system, that would be we will be using the Hartree exchange the Pauli kernel. Now there's another way to compute the Pauli kernel by using the difference of the inverse of the Plasmonic constant response function and the inverse of the constant response function, where we can approximate this using the linear response function. In this case, what I'm going to be focusing is using the frequency independent kernel for Pauli because we want to study collective excitations. So let's see how Orbital-Free TDDFT performs in the calculation of getting the optical spectrum of a cluster. So these results that I'm showing are in here. I'm taking the optical spectrum of silver 20 tetrahedron. In this case, because we want to, let's say, propagate the system from the same ground state, we need to do an inversion to have the same initial state in the consham and the orbital-free system. We can see the dashed line is a linear response consham, and the red continuous line is a linear response orbital. In both optical spectra, we can see two plasmonic peaks, where the first one is in better agreement than the second one. And we can also observe the transition densities for the first plasmonic peak given by orbital-free and consham, which we can see a similar distribution of the electron transition density in space. And we can also observe the second plasmonic peak, which has, in both cases, like a quadruple distribution of the electron density. Now, what happens if we scale the electron-electron interaction? So we want to see how the electron-electron shifting the interaction of the electron-electron kernels, shifting the interaction of the electrons affect the position of the plasmonic peaks. So now we've seen that for the fermion constant system, if we completely remove the electron-electron interaction, so the Hartree and the exchange correlation, the type of excitations that we are going to observe are single excitations. So we must have these kernels. For the boson constant system, if we switch off the electron-electron interactions, the type of excitations that we should be observing are plasmonic excitations. So let's see what happened in this case. This is a plot where I am plotting the lambda parameter, where 0 is the non-interacting case, 1 is the interacting case, and this is the position of the frequency and electron volts. For consham, when lambda is 0, we can see that the plasmon peak is around 2.25. When we put the interaction on, then we recover the first plasmonic peaks. And the shift is around 1.35 electron volts. For the orbital-free DFT system, we can see that we start from a higher energy, the plasmonic, and then it goes to the correct position of the plasmonic peak, but the shift in the frequency, in the energy of this plasmon peak is 0.25 electron volts. It's much smaller than the shifting of the consham plus the first peak of the plasma, which is an indication that the boson constant system is a good system to study plasmons. Now let's see what happened for the computational efforts, saying like how big the Cassidy matrix needs to be to observe these plasmonic peaks. In this case, I'm gonna do an analysis of number of states given by occupation standard rules.
Sorry. So when lambda equals 0, then you should have, it's a non-interacting system.
Yes.
So consham gives you then the first consham excitation. Right?
Yeah.
When you do the orbital free, you have the polycurnel in there?
Yes. You just shift the hard to exchange correlation.
Yeah, hard to exchange correlation is gone.
Yes, and
But the polycurnel should then make it equal to the Colchamp response function. If you have the exact polycurnel.
yeah, but in this case, we're using the adiabatic approximation. It's frequency independent.
So you're saying that shows us that then that the polycurnel is very non-adiabatic.
Yes.
Right? Because this is not close at all.
Yes.
Yeah, exactly.
So the point is that if FP was exact, you would be on top of Colchamp.
Exactly.
Yeah, exactly. And that blue dot where it says B is
Yes.
way up there.
Absolutely.
Yeah.
So then the question is, why are we doing this? And the reason is that we're targeting collective excitations. And collective excitations for the orbital-free system, they are already recovered at the non-interactive level. Because the HOMO is occupied n times, and when you do an excitation on LUMO, you are exciting collective excitation of all the electrons from the HOMO to the LUMO.
Okay, but that's a bit strange though. I mean, it's so you're saying
I'm
somehow
saying
that somehow indicates that in the orbital-free case, the exchange correlation makes a much smaller correction because you already you show this delta, no? That's 0.27, 0.75. Whereas in the red case, it's 1.35. So it's a huge correction.
Yeah. Essentially, by choosing the Colchamp system, you're making kind of like an odd choice for plasmons. Instead, you should really choose the boson Colchamp system if you're targeting plasmons. It's kind of like the most inconvenient basis is to use the fermion Colchamp system for plasmons.
I thought of it that way. I hear what you're saying. So, anyway, sorry, we can keep going.
And okay, so now we are gonna analyze how big the Gaussian matrix should be to capture the first plasmonic peak. So the blue dots again show the orbital-free, the position of the first plasmonic peak for orbital-free system. And we can see that we already have a good agreement with the plasmonic peak with a 13 number of states, while for Colchamp DFT, we need at least 400 of states to get the correct position of the plasmonic peak. So with these results, we can conclude that the boson Colchamp system is a good system for studying plasmonic nanoparticles, and we will continue doing this type of work to show more to the community, and that's it. Thank you.
For 2 electrons, does your bosonic system is like 5-0, 5-0, right? This is similar to the Colchamp thing, right? And then your excitations would be like double excitations. All your excitations are pure double excitations.
Yes.
Yeah. Right. So then I guess the question is, what do you, in order to get single excitation, like it's
Very non-adiabatic.
Yeah,
it's funny, isn't it? Because it's the reverse problem.
Yeah, reverse problem.
we have to add, yes, we will have to add the frequency dependence of the polycurnel and all the
And the inverse. Is there a way also to find out whether, for simple systems that you could do some analysis to figure out what the exact frequency dependence looks like for FP? And if it's harsher or less or something.
Go to the slide of Kai Beamer's.
Yeah, so this could be a way to approximate it using the response function. But again, in orbital-free DFT, we don't have the Colchamp orbital. So we would approximate the Colchamp response function with a linear response function. But this would be like the first.
Right. No, I mean, I guess if you had some system that you could solve.
Yeah, if we had,
Yeah.
we could
Yeah.
do it.
So we did it for the uniform electron gas.
Right, I see.
And you can see
Yeah.
some stuff.
Yeah. And how does it compare to because this is the object that would have to be, approximated in general. So
Yes.
how is its frequency dependence compared to the frequency dependence in
Actually, very simple. The terms are, in some sense, they're comparable. Like you have a term that goes in, like if you do a Taylor expansion, for example, around omega equals 0 and Q equals 0. In a certain limit, you can do that, and I mean, you can write something that then you can code.
although those limits don't compute.
Yeah, the limits don't commute.
So-
Yeah, so you pick one, and
Yeah.
that's usually.
There is no more question.
What do you mean, no more question?
Yes, but if you have one question, go ahead.
I'm sorry.
Sorry,
Like two more, right? The first one is, so this is all finite.
Yeah, so for
variables, extended systems,
disaster,
periodic systems.
problematic.
Yeah.
There's a
in what way?
huge problem of ensemble and representability for orbital-free that nobody knows about
Oh.
for extended systems. And that's why we're not touching them yet. But we can certainly talk about it.
Did you run into it yourself?
Oh, yes, so we have we've showed that the problems is there already with a silicon or even aluminum, or already with a cell with 32 atoms you have.
So meaning you can't find the bosonic system, or like it doesn't exist.
It's a deeper conversation that if you wanted to find the bosonic system, you would have to use, in the limit of a very large system, you have degeneracies that are below any machine precision which you can possibly have in your computer, and therefore you have to use ensemble. But this is true also for Concham, I think, right? When you have degenerate levels at the Fermi level, you smear those levels, yes? So we haven't touched those systems from in a formal way because of that.
If you manage to solve that problem, I would then. Sorry, this discussion. So now then you could ask what happens if, or can you describe systems with a gap?
Well, all these systems have gap. The first plasma, the first peak, the first collective excitation has a gap.
Yeah, but what I'm asking is there are collective excitations that are not plasmonic in nature.
Okay.
Right? So I am
Interesting.
like accidents.
Tell me more.
I
Okay.
like accidents, which I will tell you all about tomorrow. They are collective excitations. So
There are
you should be able.
some parallels.
I bet there are parallels. Super interesting. Sorry, last one. Can you do real-time orbital-free TDDFT?
Yes.
We started with that.
Yeah,
Yeah.
where
And
the
then
thing, yeah, you give it a kick and it starts
Yeah.
doing that.
Yeah, she has actually all her plots used to have both real time and Casida, and I told her to just shortcast them.
Nice.
But we don't have it.
Published? Not yet.
Yeah, published
Published.
2 papers, 3 papers.
With the
I should have known
3
that.
papers.
I'll check it out.
So we can go speaker again.